Okay, so let's review. Let's review last time. So you're asking about Petersson products. So if I have F and G are modular forms of weight K, then I would like to know how to write down their inner product. And if I just say, well, you integrate over a fundamental domain, our nice fundamental domain, D is a domain for SL2, well, upper half plane, let's say, upper half plane mod SL2Z, gamma is SL2Z, of F of Z times G bar of Z times dx dy over y squared. So this is an invariant measure. I want to be able to integrate over the quotient, but this thing is not invariant. I have to say how to make it invariant. And the way to make it invariant is to multiply each of them by y to the k over 2 and one with a conjugate. So if I multiply by y to the k, now this thing is an automorphic function. This is invariant under SL2Z.
And that's basically what you're asking for, right? If you're doing the Petersson stuff, we want the inside to be automorphic.
Right. So that inner product depends on what the weight is. So that's why there's one for each weight.
And you can multiply forms with different weights, right? You just have to modify it.
If you want to, right? So this to be a Hilbert space, right? We want to think of the space M K gamma is the vector space. This is a vector space of weight K forms, modular forms.
Right. I mean, you can remove K and do general stuff.
So if you have F of weight K and G of weight L,
right,
you certainly can form the inner product. You certainly can form the integral F times G bar times y to the K plus L over 2 dx dy over y squared. Yes, you can certainly do this integral over H mod gamma. And it makes complete sense. But as an inner product, usually we think of inner products on a Hilbert space, like a vector. This is a finite dimension. In this case, it's finite dimensional vector space.
right.
And so we would like the two things to live in the same vector space.
Some case.
You mean, okay, so you want an infinite, you want to look at the space of all M of gamma, which is the sum over MKs, right? Like a graded ring. Okay, the problem is if I take an element in here, if I take two elements in here, well, first of all, there are arbitrary linear combinations of different weights.
Right, so in each weight we do this,
But
on each pair of weights.
But then I have to know which weight it is that needs to be. There's a different formula for F depending on which component it came from.
But that's not the problem.
It's basically not a problem, and that's what representation theory will allow us to do. This discrete series representation will have all the weights, but of a single form, moved by raising and lowering operators.
Okay, so
But it's different from taking just an arbitrary sum like this.
So we'll see when we get there.
Yeah.
Okay, and the second question is mass forms, right?
Yes.
So we mentioned that modular forms correspond to elliptic curve. What mass forms correspond?
Algebra geometrically, nothing. That's what makes them so much harder.
But the Langlands correspondence or something should map onto something, right? Or
So okay, depends on which Langlands you want to think about. If you're thinking about algebraic Langlands, which is there should be for any nice algebraic object, there should be a corresponding automorphic object that captures.
There should be a mapping for a function.
Yes. So there's nothing on the other side of that correspondence for Langlands for Moss forms. Because these are transcendental, that entire story is an algebraic story. And this is the transcendental story. And in fact, the transcendental story in some concrete sense is the bulk of the decomposition of L2 G mod gamma. So almost none of what people often speak of as the Langlands program is what's in this decomposition.
This is discrete, so
That's the discrete series part.
Interesting.
So these are these things have, as we were discussing last time, these Moss forms have Fourier expansions, right? Phi of x plus iy is some sum of some coefficients, then some solution to a differential equation coming from the Laplacian, these so-called Whittaker functions of y, depending also on the eigenvalue, and then e to the 2 pi I nx. Okay, these coefficients as complex numbers and these eigenvalues, well, it turns out for SL2Z, it turns out both can be made real. They're transcendental, and as far as we can tell, and algebraically independent from any other known constants.
And okay, and so you're saying versus the case of modular forms.
Versus modular forms where we can have coefficients that are integers or algebraic numbers.
And then that somehow like allows you.
That corresponds to counting points on elliptic curves, for example, which is the first thing.
Nice, nice.
Yeah, but in terms of L function, you still could build an L function.
Yes, you still build an L function out of phi, and it'll be the sum of these ANs over n to the s. It's just that these coefficients will be transcendental numbers.
So there is no representation theory object that we map.
There is a representation theory object, but there's not an algebraic object. You see, a lot of times people talk of the Langlands program as sort of algebraic, algebra geometric, algebraic objects on one side and representation theory objects on the other side. For example, Galois representations,
Right.
finite dimensional representations of the absolute a Q bar,
Okay.
over Q, right? There is no such story for Moss forms. Moss forms are transcendental. And again, if you look at L2 of SL2R mod SL2Z, the bulk of this decomposition is the transcendental guys, not the guys that have anything to do with algebra. But there's still a Langlands program for these. This is the functoriality principle, that when you apply representations to these, so this is a form, the form generates an irreducible representation, well, the principal series representation. This is an irreducible representation of SL2Z. So the group G, SL2Z, acts on this infinite dimensional vector space. I haven't explained how this is done. And it has an L function, and this is the L function. So the L function of this pi is this classical way of constructing L functions by just taking the coefficients, sticking them into a Dirichlet series. And the functoriality program is to replace pi by some representation of pi, like the symmetric powers, symmetric power representation. I haven't explained any of this, so this is all what's coming later. Bless you.
Okay, once we get later.
Well, let me give you one example of the kind of thing that we would like to know for Moss forms that we do know for elliptic curves, for example, precisely because of this algebraic relation that we don't know for Moss forms because we lack such an algebraic
So
relation.
here in the Moss form stuff, you're sort of saying the more algebraic side is going to be this graph theory setting.
Well, the whole thing lives here. There is no corresponding object on this side.
Okay, we'll get there.
Yeah, let me say one thing, which is the Ramanujan conjectures. Okay, so the Ramanujan conjectures. Ramanujan for the discriminant function. So we've seen the discriminant function, this q times the product of 1 minus q to the n to the 24th power, right? Which we talked about this, I think, several. Yeah, a little bit, right? It's if you multiply this out, you get a q and you get a 24.
Open house.
Right. Okay. 24q squared plus and so on, right? It has this q series expansion, which is a sum of tau of n q to the n. I think we did talk about this.
Yeah.
And Ramanujan conjectured, specifically in this setting, this is the Ramanujan tau function, the tau of p is bounded by 2 times p to the 11 halves. Okay, this 11 halves is 12 halves minus 1 half. And 12 is the weight. This discriminant, delta is weight 12. And so this minus a half, this square root cancellation in the exponent is a kind of Riemann hypothesis. And this was proved by Deline. And the analog of that, now the 12 halves you can prove trivially. If you just want this bound, it's very easy to prove this bound. This is the so-called trivial bound. The analog of that for Moss forms is that you can trivially prove that these ANs grow at worst like n to the 1/2. N to the 1/2 is the analog of
And then for,
yeah.
What does the Ramanujan say for general?
So the conjecture is that actually these grow no faster than n to the epsilon. In fact, the p values, the prime values, the only reason you need epsilons is because lots of primes could multiply into n, and you get these twos catching up to each other, that these are bounded. So that this Dirichlet series has an abscisive convergence, which is s equals 1. You see, the growth rate of this tells you where your Dirichlet series converges initially.
Well, I
Right?
guess I meant like the general Ramanujan is.
Yeah.
The Titus is known for n, not this.
Yeah, so by multiplicativity, tau of n is then bounded by like the divisor function of n, the divisor function of p being 2. This is bounded by, this implies, this plus multiplicativity implies that tau of n is bounded by like the divisor function of n times n to the 11 halves. And the divisor function is bounded by n to the epsilon, the number of
Really
halves.
all.
Yeah, all you care about is what happens at the primes. I mean, I can tell you what's really going on if you want. Let's forget about everything that I had planned for today. What's really going on, okay? And I mumbled this when we were talking about elliptic curves, however long ago. What's really going on is that this is an L function of degree 2. This is a degree 2 L function. L function. So L of phi of S. It looks like a Dirichlet series, but the better way to think about it is an Euler product. Let's take a Moss form. Let's take a Moss form on GL2.
Okay, he's general, in general, we
No, in general, if you're on GLN, it's going to be degree n.
well, I mean, like in general, in GL2, I guess, if you take an arbitrary number.
Yes.
in GL2.
Yes, it's going to be a degree 2 L function, which means that its Euler product has 2 Euler factors, alpha p over p to the s, and 1 minus beta p over p to the s inverse. So if you think about what this means, if you multiply this out, this quadratic polynomial, you get 1 minus alpha p plus beta p over p to the s, all inverse, plus alpha p times beta p, alpha p times beta p over p to the 2s. So it's a quadratic polynomial in p to the minus s. Okay. And on the other hand, you have this expansion, which is a sum over now these ANs, okay, if this Moss form is also an eigenfunction of the Heck operators, which we haven't discussed yet, then these ANs will be multiplicative. And if they're multiplicative, then I can say this is a product over primes. So degree 2 L function. Phi is a Hecke
And then
eigenform.
again, in studying the behavior for the primes, will again, resolve in the same way that they're,
Yes. Yeah. Yeah. So we're going to get a sum. Let me just write this as a sum. 1 plus AP over P to the S plus AP squared over P to the 2S plus and so on. Okay. Let's have a division here. So what I'm saying is this Dirichlet series will factor into products over primes of Dirichlet series corresponding to that factor. And it will turn out that that Dirichlet series will be a quadratic polynomial. There's the Hecke operators at not prime places. Well, what do I want to say? It will turn out that AP is a product of is a sum of alpha p plus beta p, and that AP times BP will be in this normalization will be 1. And alpha p times beta p in this normalization is 1. Okay, so I have two numbers that multiply together to give me 1, and they add together to give me AP. So how can two numbers multiply together to be 1? Well, they can be complex on the unit circle, or there can be one that's B is 1 over alpha B. The sum, by the way, these APs are real. So that's something that I have to justify for you. So how can two numbers multiply to 1 and add to a real number? Well, they can both be real, and one is here at 10 and the other one's here at 1/10. That's one option. Or one is over here alpha and the other one is over here alpha bar. Beta is alpha bar, and their absolute value is. The imaginary parts have to cancel out. Either there are no imaginary parts, or they're complex conjugates because their product is 1. And so what Deligne proves is that this doesn't happen. That alpha and beta are on the unit circle. And if alpha and beta are on the unit circle, then their sum, so then AP is at most 1 plus 1, which is 2. So that's what this 2 is. There's a scaling you have to do to see that 11/2 is the right thing to divide by, so that your functional equation is 1.
That where the work of the proof is showing that.
Yes. Everything that I've done is the triviality. This crossing this out is what you get a Fields medal for.
So this takes all from the representations for billions on the portion which is two-dimensional.
So you mean, how does Deligne actually do this? So it actually uses, so let me come back to that question in just a second. So what Langlands says is that when you play games, so these are called the Langlands-Satake parameters. These alphas and betas are called the Langlands-Satake parameters. Langlands-Satake parameters. And what people were trying to understand, so there was a red herring, basically. The red herring was that Rankin and Selberg explained how you can get L functions where you play on the Fourier coefficients. So Rankin-Selberg.
Instead of like this, multiplying modular 1.
Yes. So Rankin-Selberg says you can create the sum an squared over n to the s is an L function, It has a functional equation, it has an Euler product. Okay, has a functional equation and Euler product. That's what I mean by is an L function. I mean, of course, anything is a Dirichlet series. But what do I mean by an L function? Has analytic continuation, function equation, and Euler product. And so people thought maybe what you're supposed to do to get more information. Oh, and there's information that comes with this. The fact that the an squared is an L function, and you can see that this thing has no poles and converges absolutely down to s greater than 1. Those two pieces of information, or I have to get all these normalizations right. Those two pieces of information take you from the trivial bound of an is bounded by n to the 1/2. So the Rankin-Selberg method will tell you that the ans are bounded by something like n to the 1/4. So they make some progress towards the Ramanujan conjecture that the growth rate is not 1/4 but epsilon. In other words, 0. And so people thought, so there was a hope that if you could make sense of something like an cubed over n to the s, if this was an L function with a functional equation and an Euler product, then you would reduce this down to an is bounded by n to the 1/6. And if you could do to the 4th power, you could, if these other L functions, if these other Dirichlet series were L functions, then you could whittle your way down to n to the 0, which is a Ramanujan.
You can't like iterate this. You can't take the an squared L function and then Rankin-Selberg it.
No, because the an squared L function will be an L function of degree 3.
Right. This is the new numbers.
So, and that L function was conjectured at the time, or I don't know if it was, Rankin-Selberg long predates any of these things, but let's be ahistorical here. You could say that this degree 3 L function, we now know by a converse theorem, we now know that that degree 3 L function is the L function of an automorphic form or automorphic representation on GL3. So this game on the Fourier coefficients does take you from a GL2 automorphic representation to a GL3 automorphic representation.
But it doesn't stay like in this.
But that's not true for the cubes. and the fourth powers. And so this thing is not an L function. In fact, this does not have analytic continuation.
Really?
Not have analytic continuation. Yeah, you can actually prove this, have analytic continuation.
This is kind of actually a nasty object, even though it looks similar to the other.
It looks similar to the other one, and it's the wrong kind of object. Okay, so this is the wrong object. What's the right object? This is where Langlands, as I see it, he has this whole thing called Euler products. He has a series of lectures called Euler products. And the right object is to play games on the Langlands-Satake parameters. So this series is also a product, it turns out, of 1 minus alpha p squared over p to the s times 1 minus alpha p beta p times p to the s times 1 minus beta p squared over p to the s. Okay, yes, it's actually the way I've written it. It turns out, so this isn't the Rankin-Selberg square of two L functions. If you had, this is the Rankin-Selberg, this is really the symmetric square, which is a degree 3 L function.
Yeah, because I'm thinking of the one you could roots and multiply them all.
That's right. That's right. So this is, here I have just one set of roots. And what I'm doing with them is called the symmetric square representation. So I've taken the alpha p and the beta p from a degree 2 L function, and I've turned it into alpha p squared, alpha p beta p, and beta p squared into a degree 3 L function. Have I lost everyone? No, it still makes sense. So the right object, instead of trying to do something on the Fourier coefficients, is to go one step further. What's the symmetric cube representation? It's this, a product over the primes, 1 minus alpha p cubed over p to the s, 1 minus alpha p squared beta p over p to the s, 1 minus alpha p beta p squared over p to the s, 1 minus beta p cubed. Exactly, that's exactly what it is. It's symmetric polynomials. I mean, that's what the symmetric cube representation is. So this will be conjecturally the L function of the symmetric cube of the representation at S. Thank you, cube.
And this is the conjecture.
The cube, okay, so this is where we get to Kim Shahidi. So for GL2, for Kim, so this L function we know to be an L function. The symmetric fourth power we also know. So this is Shahidi and Kim Shahidi.
So where are we running to studying this object?
We want to know that this object has a functional equation, has analytic continuation and functional equation.
And that would resolve what?
That would allow us to bootstrap. That would allow us to get better and better bounds, actually, towards the Fourier coefficients. So what we currently know, so this is due to Kim's. So these exotic objects are found in the E6 and E8 representations in very complicated ways. This is the Langlands-Shahidi method for constant terms of Eisenstein series having L functions in them, and using functional equations of Eisenstein series to prove functional equations for L functions. And if you have enough functional equations for L functions, the converse theorem tells you that there is an automorphic object. I'm throwing so many words at you. I think this is just, word salad at this point. But
No,
but-
I mean, I'm taking the other aspects.
Yeah.
That's so something we could just.
Yeah.
bash.
okay, so the best we know, so finally Kim, and there's an appendix by Kim and Sarnak, show how using these lifts, the known lifts that come from these exceptional groups, you get the bound. The world record right now is AP is bounded by, well, I guess the constant is 2, P to the 7/64. This is this magical Kim Sarnak number.
Oh, this is more or less one for Moss forms.
For Moss forms.
Okay.
For Moss forms. Well, it also applies to modular forms, but we have much better bound for modular forms.
So this is
Yeah.
like one very much unsponded.
Right, it's a little bit less than an 8. You can do a little bit better than 1/8, which is what you get from the symmetric.
And what we had trivially for Moss forms
Was 1/2. Okay, so it's some progress towards It's the best known, currently best known progress towards Ramanujan. Well, they're not tight in the sense that they're not the truth, but they're tight in the sense that this is the best we've been able to squeeze out of the known symmetric lifts of L functions. But, and this was pointed out long ago by Sayre, actually. Sayre was the one that this L function or the symmetric cube,
Yes.
it's right here, so it's degree 4. So the symmetric nth, so Sayre pointed out that if we knew if this symmetric nth power was an L function for all n, if you had all of these lifts, if the symmetric nth representation is automorphic. He didn't say it this way yet because this was before Langlands. It was around the same time as Langlands was building up his theory. But he made this observation: if all of these L functions are automorphic, in other words, the growth rate. It's like if you want to know that something is bounded by 1. So if you want to know that some unknown quantity, I'm just going to call it x, is bounded by 1. Okay, here's what you can do. If you know that, what you can trivially prove is that x is bounded by 10. Okay, but then actually x squared is also bounded by 10, and x to the 5th is bounded by 10, and x to the, if x to the n for all n, x to the n for all, if you know this for all n, then you know this, because the second you're bigger than 1 plus epsilon, some huge power of it is going to be bigger than 10. It's something, it's completely trivial. It's some trivial observation like that tells you that these growth rates have to be 0 as long as Langlands is right and each of these symmetric powers is actually automorphic. So this is a functoriality. It's not that it's connecting to an algebraic object on the other side. It's that it's connecting to itself, bootstraps of itself. So Sayre says, sorry?
Does Langlands care about his functoriality?
Yeah, Langlands is the one that proposed that these things are actually
Goes that and
also this other stuff and global, and then people, local Langlands, and then mathematical physicists got involved. Yeah, there's a whole long story. So Sayre says if these representations are all automorphic, then you get Ramanujan. That's a way to solve Ramanujan's conjecture.
Okay, and so we know this with 3 and 4.
We know these symmetric lifts, yes, the symmetric cube and symmetric 4.
This is going to be like a converse theorem thing, like you have enough of these and.
Right, if you have enough of these twists, then you get automorphity. We've run out of exceptional Lie groups. So this method stopped. There is no E10. So we're not going to find the symmetric 5th power in there.
Like, you need to find the right objects to work on.
Right, you need to, if you want to continue this method, I mean, there are other methods as well.
Sometimes you want some method and dumped up, right?
That's right. And we're stuck. We're stuck. We haven't found methods that do that. You can write down the diagram, but it has an infinite file group. It's not a finite file group. So to answer your question, so Deligne actually took inspiration from Langlands' conjectures to find on the Galois representation side. Yeah, maybe that's not the right way to put it. But basically he constructs. He learns enough about these symmetric power lifts to get Ramanujan. So he's really using this bootstrapping idea. This is a kind of induction that he can execute. And today, not for Moss forms, but for modular forms, we know that all of these symmetric power lifts are indeed automorphic. And this is, Taylor and company.
That's recent.
That's much more recent, yeah. Deligne didn't need the fact that they're automorphic. He needed some much weaker information on these.
So why do the elliptic curves and like modular form case, why do the algebraists want the analysis? Why do they want?
Well, they want the Ramanujan conjecture. And the way to get it is
Going on that route.
Yeah.
And what do analysts want from like the algebraic side?
Well, what do analysts want from algebra? They want answers to their analytic questions. So there are lots of applications. You might think like, who cares about 7/64 versus there? It turns out that there are lots of applications where if you do anything better than, it's called subconvex, anything better than the trivial bound, any exponent here better than the trivial bound gives you the application you're looking for. So for example, I'm going to say more buzzwords, quantum unique ergodicity. This is something where if you had, there's a certain large degree L function, where if you had a subconvex bound for that L function, you would prove quantum unique ergodicity directly, as opposed to how Lindenstrauss proved it, which is very indirectly.
This is unique ergodicity in the sense of Einstein.
Exactly. Yeah. Anyway, have I gone on enough tangents?
No, one more.
One more tangent. Go ahead, please.
Okay, we would give the definition for the function,
Yes.
and it was a gap.
Yes.
When you wanted to talk about
Yes.
the cusp.
Yes. So let's come back to that gap. Yes, let's fill that gap. Let's fill that gap. Okay, great. So okay, so let's fill that gap. So last time we talked about the unit tangent bundle and how the unit tangent bundle was can be identified with PSL2R, which acts on, now I really do need the P so that it acts trivially everywhere, right? You remember this? We had a point Z and a tangent vector eta, and these could be gotten from taking I and the tangent vector straight up, which is also I, and acting by an element of, this is the identification. So an element G is identified with G acting on I up, and you can reach any point in the upper half plane and any tangent vector at that unit tangent vector at that. Okay. We also wrote down coordinates. So we wrote down a Haar measure. I mean, thinking about this this identification, we wrote down a Haar measure from the Iwasawa decomposition. So if we have G is nx ay k theta, nx is 1x 0 1, ay is root y 0 0 1 over root y, and k theta is cosine theta, sine theta, negative sine theta, cosine theta, right? So this was the Iwasawa decomposition. That's not an I. Iwasawa decomposition. And in these coordinates, the Haar measure dg is dx dy over y squared and d theta. And this is an invariant, yes, the Haar, in other words, invariant under all of G, the invariant measure under all of G. Okay, and so we can think about being in L2. So what does it mean to be in L2? So the last thing, so so in our definition of a modular form, if f is a function from the upper half plane to the complex numbers, it's holomorphic, so it satisfies Cauchy-Riemann, as opposed to Moss forms which are eigenfunctions of the option. It's holomorphic. I want it to be modular. So A, B, C, D, Z is CZ plus D to the K of weight K, F of Z. This is for all A, B, C, D in SL2Z and for all Z in the upper half plane. Okay. And here's the last condition. So let me define cuspidal modular forms first. And F is in L2 in the sense that the Petersson inner product of F with itself, which is the only way that I can F times F bar, y to the K, I need to know that there's a weight K, dx dy over y squared. Now I know what measure to integrate with respect to. I want this to be finite. Okay, then F is a cuspidal modular form.
But then you do the angle is
Which angle?
the theta.
Oh, there is no theta here. In fact, the theta is hiding in here. When we lift F to a function on SL2R, it will be a function that the way that it changes by theta is e to the 2 pi I theta k. It's a slightly different setup, yeah. So there's two separate things. One is right. Although secretly they're not so different. Okay.
So you're saying,
Yes. So let me explain why this is what we're going to call a cuspidal modular form. So remember, we had a Fourier expansion. The fact that f is invariant under x goes to x plus 1 told us that we had an expansion in all integers z of some coefficients, which at first depended on y, e to the 2 pi I n x. And then the Cauchy-Riemann equations told us that this function had to be e to the 2 pi I n y, so that we could write this as e to the 2 pi I n z as a Q expansion. Okay, now let's think about this inner product. This inner product is a fundamental domain for this action. Now I can actually say all of these. A fundamental domain for this action we know is here. So when we take this integral, we can take the integral over this region, D. Now, if this region is finite, so is the smaller region here. So the integral, the fact that f inner product f is finite, so is the integral just over, I'll make the integral even smaller by integrating from something where I can completely separate the role of x and y. So x will go from -1/2 to 1/2, and y will go, let's say, from 1 or from 10, doesn't matter, from 10 to infinity. I'm eliminating some compact region. I'm only integrating in this cuspidal region. Okay, that's what will be a cusp point. And then I have norm f squared dx, and then y to the k dy over y squared.
Yeah, so everything's positive, y is positive, so.
Yep.
Well,
Okay, now let's think about what this integral is. I have an expansion like this. Let me write this again as e to the 2 pi I n x times e to the -2 pi n y, just to illustrate this point. If you have, so what is Parseval? Parseval's identity. Parseval's identity is that the Fourier transform is an isometry. In other words, the L2 norm in the x variable. So Parseval says that the L2 norm in the x variable, f of x plus iy squared dx integrated over r mod z, in other words, over -1/2, is exactly equal to the L2 norm in the Fourier space, which is a sum over n in z of an squared e to the -4 pi n y.
So there's an isometry between.
The Fourier transform is isometric. So whatever the Fourier, these are the Fourier coefficients. These things together are the in x Fourier coefficients of f.
Right.
This is the integral over all of r mod z in x of norm f squared.
So you can map out from this side to the other, and that's an isometry.
And this is an isometry. Or you can check this directly. Just take this formula, square it out. The integral will only pick up the diagonal terms. That's a proof of Parseval. But this is a general fact, so I do want to highlight that. Okay, is this clear? So then what happens? Now I integrate from 10 to infinity, multiply by y to the k dy over y squared. And this I'm going to integrate from 10 to infinity. Of course, I'm going to interchange summation y to the k dy over y squared. But this integral, if n is negative, or even if n is 0, this integral is divergent. This integral diverges unless n is greater than or equal to 1. If n is at least 1, then I have exponential decay in y. Polynomial growth in y, who cares? I'm integrating from something up to infinity that converges.
So we're rating your ANs were. Oh, yeah.
But this is supposed to be finite.
Right, right.
So you can't have a divergent integral here, which means the ANs must be 0, except for the positive values. So this implies AN is 0 unless N is greater than or equal to 1. Does that make sense? So in order for this L function, in order for this modular form to be in L2, to be square integrable, in the sense of the Petersson inner product, a necessary condition is that it does not have an expansion in all integers. The Q as a Q series, that implies that F of Z as a Q series is a sum as N is at least one AN Q to the N.
Wait, and back up here, these ANs, they can't cancel on assumptions going on with this.
Everything's positive. Everything's positive, and the sum is finite.
So what it means the ANs can't be like they can't force this integral to converge.
They're not involved in the integral. They're for each N, I get an integral like this. If N is 0, this thing is not convergent. Well, if K is 0, then it is. But K is 0 there are no weight 0 modular forms.
The AN can't be 1 over the integral.
No, AN. Well, if the integral is infinite, then the AN is 1 over the integral.
Right, yeah, that's what I mean. These ANs, like,
They're not functions of Y.
yeah, they're finite, so.
Well, whatever they are, they're constants independent of Y. This is an integral in Y. I can't have divergent integrals summing to something that's finite unless the coefficient in front of them is 0 and they were never there in the first place.
Right.
So this is what I prefer as the definition of what's left over. What's left over should be that the Petersson norm is finite. That defines cuspidal modular forms. And then you do want to allow non-cuspidal modular forms. You want to relax this just a little bit, but not so much as to have actually divergent integrals here. Well, they're still going to be divergent, but if F has at most polynomial growth, this is called moderate growth, at most polynomial growth, as Y goes to infinity. This is called moderate growth in the literature. Cuspidal.
In Fourier, this is first mouse and greater equal to 0.
Exactly. And this is equivalent to AN is 0 unless N is, I'm allowing 0. I'm allowing a constant term. Even though the constant term will not be square integrable. Right? There's a y to the k in front. That constant term is not going to be square integrable. And this is where Eisenstein series are of moderate growth, but not cuspidal. So these things called Eisenstein series, which I don't think we've discussed here yet, are modular forms, which are.
I gave the example of delta.
I gave you the example. Well, delta is cuspidal. Yeah, delta. If you notice, delta. Where was it? All the way back here. Delta is cuspidal. It starts at 1.
You name drop like an E4, E6, I guess, but
Oh yeah, we did discuss E4 and E6 because they arise in the distances, the set of points in E8 at a given distance from the origin. Those coefficients. What's that? No, but that's the Eisenstein series. No, not the E8. E8 is not an Eisenstein series, but E4 is the weight 4 Eisenstein series, whose Fourier coefficients are telling you how many E8 points there are.
terrible meaning system.
What can I do? Eisenstein E is exceptional, although it's not really exceptional. It's because there's type A, B, C, D, and then type E, and then there's type F and type
At
G.
some point, people should go in and like just clean up the literature and like choose the.
It's impossible. No, it's impossible. There's too many things already here. Okay, so have I now fixed the gap?
So F is going to be, it's not going to have a norm, right? Because,
In general, F will not have a norm. The cuspidal ones will, an L2
Right.
norm.
let's say moderate but not cuspidal.
Yes.
So there is no filter space, because it's not good. The space is there. But
The space is there. It's a vector space. It's just not a vector. These are not L2. They're not square integrable. They're L infinity. They're bounded. They're bounded in the compact part, in fact. So yeah, so one thing that you okay, so let me say, moderate growth implies bounded, actually. So there will be L infinity, because if you're cuspidal, then you have an e to the 2 pi, you have at least some exponential decay. And so as you go to infinity, here, you're going to 0. If you're not cuspidal, you're going to a constant. You're going to whatever A0 is. So you're bounded. You're bounded in the compact part, and in the non-compact part, you're still bounded. Okay. Good. Any other questions? Is there anything else that I wanted to say that any other loose ends that we need to follow down?
And then we want to deal two.
Now I want to go to the Adels. Let's go back to the Adels.
You see the decomposition stuff.
Yeah. Good. Let's go. Okay. Let's start the today's topic with 20 minutes left. So let's recall a couple of things. We have our Adels. Adels are the reals and a product over the p-adics, but restricted product, all but finitely. So this is the set of A infinity, A2, and so on, where for almost all primes, AP is in the compact, the maximal compact subgroup of QP, namely ZP. The rationals are discrete. I'm reminding you things that we talked about in great detail, but it was long ago, so maybe it's not a bad idea to have a refresher. In A,
Let's use these funny ones.
oh, strong approximation, and yeah,
Stronger approximation.
right. And so a fundamental, so let's do the strong approximations. The fundamental domain, a fundamental domain for the quotient. Anybody remember what a fundamental domain for the quotient was? So the Adels mod Q is a finite interval because it's R mod Z in the infinite place, and then ZPs at all the other places. And then we had a fundamental domain for the Edels modulo the multiplicative rationals, of course, embedded diagonally. Exactly. This is a fundamental domain for R cross mod Z cross, because the only thing in Z cross, the only invertible integers are 1 and -1. R cross is the non-zero numbers, and so up to that you can make them positive, for example, cross a product over all primes of ZP. Cross.
Yeah.
Right, the units, the p-adic units in each place. Okay, we remember this. Let's talk about SL2 QP. Well, actually, let me talk about GL2R. Let's talk about GL2R first. GL2R. So we're happy with SL2R. We've been doing a lot of things. Why GL2? Well, it turns out that it'll be very annoying in our Iwasawa decomposition, which was here a second ago. Where is it? Here it is. In this decomposition, you see, if I want to force the determinant to be 1, then I have to take root y and 1 over root y. Is that a 1 over? Heck is that? 1 over root y. Okay, that's better. Root y and 1 over root y. There we go. Okay. we don't want to, when we go to the p-adic versions of these, those are supposed to be zeros. When we go to the p-adic versions of these, we don't want to think about what root p has to be. So it's more convenient to have a y and a 1, and then just remember that there's another factor that commutes with everything, which is the determinant, which will take care of the determinant. Okay, so let's pass the GL2 for our purposes. We pass the GL2, and let's work out the GL2R Iwasawa decomposition. Iwasawa decomposition. So here's the theorem. Yeah, let's say it like this. For all G in GL2R, there exists a unique decomposition of G as N A K times either plus or minus 1 and 1 times R, where Y, R and Y are positive.
So then there's
R.
Roots.
Right. So the determinant might be positive or negative. I have to take care of that. Everything else has determinant 1. Well, as positive determinant. This has determinant R squared. So so basically this follows from our Iwasawa decomposition for SL2R by saying we can take care of the determinant with these two. If you have anything in GL2 using plus or minus if it has negative determinant, or using R to make the determinant 1, we get down to something like this. Actually, we don't want to make the determinant 1. We want to make the determinant of R squared times Y equals 1. Where Y is the Y part in the decomposition of the SL2R part. So hopefully this is clear. We don't need to say more about this. It's obvious. Good. It should be obvious. All right. So before we do the same thing, let's think about what is GL2 of QP. What does that even mean? So it's matrices A, B, C, D, where A, B, C, D are in QP. And then what would it take for this thing to be a group? I need to be able to take inverses, right? The inverse matrix. This is just an algebraic fact that the inverse of this 2 by 2 matrix in any ring is DA negative B negative C, that this thing times this thing will give us the determinant on the diagonal. So if I divide by the determinant AD minus BC, this thing times that thing will be the identity matrix. So I have to be able to divide by that. Now QP is a field. It's the field of p-adic numbers. Exactly. So I need AD minus BC to be in QP cross. In other words, the p-adic norm has to be non-zero. Okay. Equivalently, this thing is in, the determinant is in QP cross. Okay. This forms a group in exactly the same way that GL2R forms a group. We can invert. I just told you how to invert because we can divide by non-zero numbers. It's a general construction. That's right. Okay. What is the first step that I want to think about? And this is where, so this, calling this an Iwasawa decomposition is kind of silly because it really is the QR decomposition in high school linear algebra or whatever. You multiply by compact, you multiply by an orthogonal matrix, right? This is an element of SO2. You multiply by an orthogonal matrix. And you get something nice. What's the analog of an orthogonal matrix here? This is where Iwasawa had the big observation. The orthogonal matrix is the red herring. The compactness is the important thing.
That's why it's named. Okay.
Right. So this is a maximal compact group. What do you think is a maximal compact subgroup of GL2QP? Is it O2QP of some kind? What's the maximal compact of QP itself? Right, I didn't say what the topology on. The topology is you can think of this as sitting inside 2 by 2 matrices in QP. And the topology is the induced topology. Yeah. That's right. That's right. So what's our maximal compact group? We can call it K sub P if we want. Yes. GL2ZP. ZP is compact in QP. This is the right analog, not some orthogonal group. It's still GL, just replacing the field QP with its maximal compact ZP. That's that's why I think this is rightly called Iwasawa.
It's like maximal in the sense that you can add more stuff.
That's right. That's right. And still have a group.
You can have like shifts of ZP, right? And those are also.
Yeah. So anything that contains this group and is compact. So if you contain this group and some other element and you're a group, then you get all the way up to a non-compact group. Let me not take the time to prove that for you. That's not hard exercise.
Not very.
I mean, in the same way that ZP is a maximal compact subgroup of QP. Why is that true? Well, if you have anything outside of ZP, you start taking multiples of it, and you get, that P will get arbitrarily far out. One over P times ZP. Oh, okay. You're saying, yeah. As ZP as an additive subgroup of QP. Right. So 1 over P times is still a copy of ZP. It's just a shift.
Right.
It's just a shift. But here we're GL2, the action of GL2 multiplies and adds. So, right, the action, it's an algebraic group, which means there's a polynomial telling you how to multiply matrices, which is the usual matrix operation that involves addition and multiplication. So once you have anything else here, it's going to start multiplying. Okay, so now we can state our Iwasawa decomposition. Oh, let's say what that is. What is GL2ZP? I mean, it looks like it's clear, right? We have elements A, B, C, D, where A, B, C, D should all be in ZP. And what? And just this, right? The determinant is non-zero. If the determinant is non-zero, and I take my nice ZP valued matrices, and I divide them by the determinant, do I still get things that are in ZP?
Yes, I mean,
Not necessarily. I might get out of ZP. So how do I guarantee what's the largest thing that contains things that look like this but forms a group? I have to make this inner product 1. This thing has to be a unit, a p-adic unit. Right. The difference is, yes, GL2Z, right. It's like GL2Z, exactly. It's like GL2Z where you have to, the determinant has to be plus or minus 1. Has to be a unit in the integers. And here, this thing has to be a unit in the integers. Here, this thing has to be a unit in the field. To be a unit in the field, everybody's invertible except 0. Okay, so let me just make that little observation. And okay, and let's prove the Iwasawa decomposition. Iwasawa decomposition. Yeah, I mean, it's none of this is hard. It's just if you mess around with it long enough, you'll find all of this.
You've come a long way in that sense, right? Observations like this.
That's all of math. Yeah, I think Conway said all of math is locally trivial. From one step to the next, it's just some very simple observation. Of course, you make a whole list of silly observations and you get to something profound.
So what point are people looking at GL2s?
Good question. Certainly by the 60s. So Gelfand, Greif, Petersson, Shapiro, worked all this out. I think Iwasawa was looking at this in the 50s. Tate's thesis, 1950. Yeah, and Iwasawa had a lot of those same ideas around the same time, actually. Just there wasn't, from Japan to here, there wasn't as much communication as it wasn't a hyper-connected world that it is now. So it took time for these ideas to come over. Okay, so what's the decomposition? For all G in GL2 QP, there exists, and I want it to be a unique decomposition, there exists a unique decomposition of G as 1 U01. U is in QP. Some diagonal matrix, I'll call that P to the E1, 0, 0, P to the E2, and then K, where K is in KP, some GL2 ZP. So we
nice representation of these matrices, sort of like how in K for NAK when it is cosine. Really sort of
no, because these are infinite series in infinite p-adic expansions. I mean, base P expansions.
In a sense, like having this AP minus BC isn't like that restricted.
That's right.
Within, like, ZP.
That's right. It's not like there's a parametrization of this equation any longer in the way that sine and cosine parametrizes. Yeah. So so K is in KP, E1 and E2 are integers, and U we have to it will not, the decomposition is not unique unless I specify something about U. So let's try to prove this and see what we need to know about U. Okay, how are we going to make G as simple as possible? Okay, so G is ABCD. All of these are, how did we remember how we proved the other decomposition? We took ABCD and we said, well, if I put a negative D and a C here, then, or better yet, a D and a negative C, then I can fill this out with a D and a C and divide by the square root of C squared plus D squared, and that'll give me something orthogonal, and that will guarantee that I'm upper triangular. Okay. Well, what I want to do is something similar, except I can't put a D negative C here because D and C might not be in ZP. They're just elements of QP.
Right, because you're doing this process before we're doing this process to get this like orthogonal.
Yeah, so once we what we did last time is we took this orthogonal bit out, so that told us what K was. Then we got something upper triangular that told us what the diagonal was, and then what was left is something uniform. Great, we're done.
So if we were to follow this process, we want to find the appropriate K element.
Exactly. We want to find the appropriate K elements to make this thing upper triangular. Now I can't just put a D and a minus C there, because these are elements of QP. K has to have elements in ZP. So what can we do? How do we make this still be upper triangular? Yeah, if these are in QP but not ZP, well, if I multiply them by some P to the L, multiplying by P to the L will shift them over and make both of them in ZP. In fact, I can do it in such a way that one of them, so let's, what is this going to be? P to the minus L will be the, if I look at the p-adic norm of C and D, yes, is it P to the minus L or P to the L? I take the worst of these, right? So C is going to be some coefficient C minus N, P to the minus N, and so on. So if I multiply this by P to the N, I get something of absolute value 1. So okay, so L, P to the minus L is the max of these. Right. Right. So there's an N for C and then there's an N for D, and I'll call that L. So that means that P to the minus L is the, P to the L is the maximum, so that when I multiply by P to the L, I get at least one of these to be absolute value 1, and the other ones that have absolute value less than or equal to 1. Then, exactly, PL to the D, well, then the max of the p-adic norm of this and this is 1. So these are both in ZP, and at least one of them, and at least one of it is a unit, and at least one is a unit, is invertible. Okay, now I need to solve. Well, no, because I'm multiplying by the same P to the L.
What it means is you could just choose a higher power of L.
No, if I choose too high a power of L, now they both start with P's, and instead of starting with a constant, non-zero constant.
Oh, you're saying this for the
Yeah, if C starts at -2 and D starts at -3, and D starts at some D -3, P to the minus 3, well, I'm gonna have to multiply by P to the 3. Then if I multiply this by P cubed, both of them by P cubed, this starts at P, this starts at D minus 3.
You're sort of trying to guarantee that this determinant condition is going to work out.
Yes, I need to make sure that I can find, I need to solve, for example, P to the L D times, I don't know, let's call these alpha and beta, times alpha, I guess times beta. Well, okay, let's call this alpha, not beta. Times alpha plus beta times CP to the L is a unit. Well, I could make that unit 1, for example.
It's like worst. So what you're saying, yeah, the worst case, at least one of them will be in ZP cross.
Yes.
And then like.
Yes. So if this one's in ZP cross and this one isn't, well, if I put in the inverse, or let's say I don't even care that it's equal to 1 exactly, I just care that it has LP norm equal to 1. So the fact that this is a unit, the QP, yes, not LP, the QP, thank you. The fact that this one, let's say, is in ZP cross means that I can multiply it by something so that it has absolute value equal to 1. And if C times PL is already has a smaller absolute value, then adding it will still give me something of absolute value 1. And if they both have absolute value 1, then it's easy to find such a thing.
Best case scenario.
Right. But what I can't have is if L is too large, then both of these will have norm less than 1. So their sum will not have norm. Okay, so that's why I need this L to really be equal to the max, not just at most the max. Okay, so it's clear that I can find such an so find alpha and beta. Check. Okay, so we found a compact. So far we have that G times something in the compact is equal to 0, and then a couple of things. Let's call this T1, T2, and I'm not even going to name this guy yet. So far, so good. So G times something in the compact has been made upper triangular by this process. Now that T1, T2 T1 is, well, wherever it is, it's equal to P to some power times a unit. This is in ZP cross. And same thing with T2. This is P to some other power times a unit. Okay, so I can write G times K times, let me invert the units, U1 inverse, U2 inverse, times P to the minus E1 times P to the minus E2. Means that I've made the diagonal entries 1. This is equal to 1, 0, 0 times some x. I'm just multiplying diagonal entries here. So this is going to be T1 inverse, this is going to be T2 inverse. The point of writing it like this is that this is still in K. I want to separate out. My claim was that we could get the diagonal entries to just be powers of P times something in K. Okay.
What we did was, I got a little lost in the process.
Yeah.
What we did was we multiplied by this K.
By this K to make the lower left entry 0.
Yeah.
So we found some K so that we have something 0. I don't have any control on what's left. I have a T1 and T2 and something. T1 and T2 are numbers in QP. In fact, they're numbers in QP cross because their product is still the determinant, and the determinant was non-zero. So that means that each of them is, well, whatever the first digit is, they might be, you know, they might have a large first digit, a small first digit. I don't know what that is. I have no control over that. But T1 is P to the E1 times a unit, and T2 is P to the E2 times a unit. I'll take out this matrix. I want to make it now unipotent. I'll take out that matrix, but I'm going to take it out in 2 ways. Once using units, and once using exactly this P to the E1, P to the E2. Okay. So now, what do we have? Let me multiply these things back to the other side. We've written G as 1x01 times P to the E1, P to the E2 times something compact. So we're done.
Uniqueness.
Uniqueness. We have to worry about uniqueness. That compact element is really big. There's a lot of stuff that can go in there. How do we make this unique? So the big question, I'm out of time. The big question is uniqueness. Uniqueness. Is this unique? And the answer is no, it's not unique until we give more specifications on X. And it's going to take me, 5 minutes to explain what you have to do to X to make this unique. So
Why do you make the entries exactly one on that?
because the entries were T1 and T2. T1 is P to the E1 U1, which is what you get when you multiply these two together.
Yeah.
So I multiply both of these things on the right by U1 inverse U2 inverse and by P to the E1, P to the minus E1, P to the minus E2.
Oh, you're literally.
I'm just literally, yeah, just pulling out the diagonal entries and then I get something uniform. It's not unique, and how to fix this we'll do. How to fix the non-uniqueness. Sorry, I ran out of time. So that's what we'll do next time. Should I leave it as homework? Think about it. What would you do? Okay, how to fix it? Let's see. We'll do it, but here's a nice little homework exercise. How do you fix the non-uniqueness? Try if you really want to understand this, don't look at the book.